So good evening, Eddington. It's a pleasure to be here, if virtually, to tell you about the beginning of everything. And as the subtitle tells you, this should be a brief description of the origin and the very early history of the universe. Now, when we look out into the night sky, we see lots of galaxies. This isn't actually real galaxies, it's effectively a 3D atlas. Many millions of galaxies have had their positions and distances plotted, and then this simulation, or at least this virtual simulation, shows us where they are in space. And this is a sort of a fly-through, if you like. It tells us that all the galaxies in the observable universe, or at least the ones that we can see close to us, are not uniformly scattered across the universe. They're clumped into filaments, and occasionally there are regions of space called voids in which there are very few galaxies. So if we want to understand why the universe looks the way it does, one of the things we have to understand is not only the existence of stars and galaxies, but why they're scattered through the observable universe the way they are. But one of the questions I'm trying to answer this evening is, when we look out and see perhaps trillions of galaxies in the observable universe, where did all that stuff come from? All of the hydrogen and the helium that's made, all of the stars and the gas and the dust and all of the galaxies, where did all that material come from? That's the question I'm trying to answer. So we know there's a lot out there. This tiny portion of the universe imaged by the Hubble Deep Field shows thousands of galaxies, despite the fact... Would you mind muting your microphone, please? Thank you. So this tiny patch of sky imaged by the Hubble shows us thousands of galaxies, telling us that there are probably 1 trillion galaxies or so out there that are observable. So what I'm covering in this talk is I'm talking about where it all came from, the creation of the observable universe. When did it happen? Well, to the best of our knowledge, it happened about 13.8 billion years ago. How long did it take to make essentially everything that we can see? Well, it took 3 minutes to make all the ingredients, and then the ingredients slowly rearranged themselves to make the stars and galaxies that we see. Where did it happen? Well, it happened everywhere. The Big Bang wasn't something that you can point to in space, because when the Big Bang occurred, it effectively created everything, including, as far as we can tell, all of space and all of time. Why did the universe evolve the way it did from that point 13.8 billion years ago to the present day? Well, it evolved the way it did because of the laws of physics. How do we know all this? Same answer. Because of the laws of physics. We believe that physics dictates how the universe has evolved and how it is evolving. So we can think about trying to understand the universe by trying to understand the rules of a game like chess. If we take a picture like this, is it possible to work out the rules of the game? Is it possible to work out the laws that allow us to move these various pieces on the chessboard? From one snapshot, it's very difficult to tell what the rules of the game are. And it's the same with the universe. A simple snapshot, for instance, of a galaxy doesn't tell us everything we need to know. The galaxy is rotating, but we can't watch it rotate because it takes 100 million years or so to rotate once. And we haven't got the patience to sit here and watch it for a few billion years to see what it's doing. We would like to understand the universe now. So just like with a chess game, well, with a single picture like that, we can't really tell what's going on. It would help if we had a movie of the game being played. But again, we can't effectively have a movie of a galaxy or a set of galaxies simply because of the timescale. But in the case of chess, rather than having one picture, what if instead of having a movie of a game being played, what if we had 1 million chessboards, each in a different state of a game being played? Then we might be able to work out the rules of the game by watching 1 million games all being played out at the same time. And in a sense, that's what we do with the universe. We can't simply look at one galaxy, but if we look at enough galaxies, then perhaps we can get, even in one snapshot, we can get an idea of how the universe is evolving. Not only can we collect data from lots of galaxies by looking at lots of clusters and taking lots of images like this, but we realise that the more distant galaxies, light has taken time to reach us because of the finite speed of light, and therefore the more distant galaxies, we're looking back in time. So although it's one snapshot, in a sense, it's a whole series of snapshots of galaxies taken at different stages of evolution. So we can't watch them evolve, but we can look at thousands, if not millions, if not billions of individual galaxies to get an idea of how they came to be. More recently, of course, rather than the Hubble Deep Field, we can use snapshots taken by the James Webb Space Telescope, and we get complementary information at different wavelengths of the spectrum. But you might say, isn't it far too complex to try and work out the rules of the game? Chess is all very well, but surely the universe is just too complicated to work out what the rules are that dictate how the universe ended up looking like this. This is, of course, just a tiny snapshot of a little region of space in our local neighbourhood. It's not even looking outside our galaxy. This is just a little region of the constellation of Orion. Perhaps you recognise a belt star on the left, the Horsehead Nebula at the bottom, and the Great Nebula is off to the top right of this particular frame. When you look at the complexity of the universe, you might believe it's impossible to work out the rules of the game. But if we make a mathematical analogy, we realise that may not be the case. So for instance, here's a mathematical collection of coloured pixels. It's a very small part of what we call the Mandelbrot set. And it's only a small snapshot, and if we zoom in, we see more and more detail. And if we were to zoom in further by another factor of 10, or 100, or 1,000, or 1,000,000, or 1,000,000,000, we would see more and more and more detail. So you might ask yourself, well, how complicated is mathematics that would allow us to create a map of coloured pixels, not just the million or so pixels that we're looking at the moment, but bear in mind we could, if we wished, zoom in by many, many factors of billions, if not trillions. This is a near infinite set of coloured pixels. It is, in a sense, infinitely complex. And you might look at certain parts of this and say, well, is it not repeating itself? Well, no, some of these things look very similar. And if you zoom into more and more detail, you tend to see regions that are similar to each other, but they're not the same. In much the same way that one star might be similar to another star, but not the same. So this is, in a sense, a little like its own universe. It's infinitely complex, and it never actually repeats, no matter how much detail we look at. So how complex is the rule of this game? How complex is the mathematical formula that allows us to create the colours of each and every one of the trillions of pixels in this set? Well, the mathematical formula is that. I'm not going to explain what the Z and the C refer to, but it's a relatively simple formula that allows us to generate an extremely complex pattern. And that simply reminds us that just because something looks complicated or complex does not mean the rules of the game are beyond our understanding. Einstein summarized this very nicely. Complexity is not the same as incomprehensibility. He said the most incomprehensible thing about the world, and for world you can substitute universe if you like, the most incomprehensible thing about the universe is that it is comprehensible. There's no particular reason why mankind should be able to understand the universe, and yet, given some thought and a lot of observation, we can start to understand how the universe works. So what's the flow of thought that allows us to get an idea of how it all began? Well, for the last 100 years or so, we've been observing that galaxies are moving away from each other. We conclude that the universe is expanding, and as far as we can tell, has been doing for the last 13.8 billion years, and again, as far as we can tell, will continue to do so for many billions of years into the future. We can do experiments on Earth. We can observe how matter is put together. We can understand the properties of matter, the properties of fundamental particles that make up atoms, that make up molecules, that make up us, and they make up the rest of the world around us. We can do experiments on particle colliders, such as the Large Hadron Collider, the LHC, and that helps us understand the way particles interact with each other. But we do have to make some assumptions. We have to assume that when we're putting together our understanding of the laws of physics, we have to assume that the laws of physics in one place are the laws of physics in another place. If the laws of physics in England were not the same as the laws of physics in Australia, we would have great difficulty in trying to understand anything. Similarly, we have to assume that the laws of physics now are the same as the laws of physics have been in the past and will be in the future. If we try and understand something and then we are told that the laws of physics are going to be different tomorrow, we will have no chance of understanding the way the world works. So there's no way we can prove that the laws of physics are immutable, but we have to assume that to make any progress whatsoever. Putting all of that together, we conclude that the universe was created in a very hot, dense state 13.8 billion years ago, and it has been expanding and cooling ever since. That is the model we have that explains why the galaxies are moving apart from each other. And our laws of physics help us construct what must have happened 13.8 billion years ago. But the big question is, where did all the matter we see today come from? When we look out into the universe, we see 1 trillion galaxies. Maybe each of them has perhaps 100 billion stars, and those stars have probably quite a few planets, and there's loads of gas and dust floating around as well. Where did all that stuff come from? One question we can ask ourselves is, how far back in time can we go before we say, well, we're not absolutely sure the laws of physics as we understand them today still hold? How far back can we go before we have to put hand on heart and say, we're not sure what happened? Can we go back to the first year of the 13.8 billion year history of the universe? Yes, the first year, no problem. What about the first day? Yes. The first hour, yes. The first minute, yes. The first second, yes. The first millisecond. Do we think 1 millisecond after the Big Bang we know what was happening according to our current understanding of the laws of physics? Yes. What about the first microsecond? Yes. What about the first nanosecond? Yes. What about the first picosecond? No. The first picosecond is the watershed. Before that, we're not actually sure what happened. Before the first 1 trillionth of a second, 10 to the minus 12 seconds, we are on slightly shaky ground because we cannot make any observations that we can prove in the laboratory. After that point, everything from 1 picosecond onwards, we can test our ideas by, for instance, accelerating particles in a particle accelerator to see how they behave, and we can start to build up a picture of how the universe evolved, but only from 1 picosecond onwards. That might sound close enough to zero to make no difference, but to a physicist, it matters. So that was a very long introduction to what it is I'm talking about this evening. I'm going to cover in one slide or so a few basic ideas that will help us understand what's coming next. And then I'm going to cover what happened in the first fraction of a second, the first few seconds of the universe, the first few minutes of the universe, and then I'll change tack slightly and jump ahead 377,000 years. That's not an arbitrary number. There's a reason for choosing that number. And then again, I'll change gear a second time and jump to the present day, 13.8 billion years from the Big Bang. So first, a few basic ideas, some of which you probably already know. We are made of atoms. I hope that doesn't come as a surprise to any of you in the audience there. An atom is a nucleus, a positively charged nucleus with negatively charged electrons buzzing around it. The nucleus is not a fundamental particle. The electron, as far as we know, is fundamental. Fundamental simply means it hasn't got any size and it hasn't got any content. In other words, an electron is not a sphere that you can cut in half and look inside and say, what are electrons made of? As far as we know, you can't do that. An electron is simply a particle with no finite size. A nucleus, on the other hand, the large mass in the middle of an atom, is not fundamental. It is made of something. You can, in principle, ask what is a nucleus made of and ask about its constituents. And it turns out a nucleus is made of protons and neutrons. We found that out quite a few decades ago. And we can ask the question again, are protons and neutrons fundamental, or are they made of something else? Can you take a proton and look inside to see what it's made of? And yes, you can. And it's made of particles that we call quarks. We're not going to worry about why they're called quarks, and we're not going to spend any time worrying about the properties of quarks. We're simply going to say that quarks are fundamental particles, and when you put three of them together, you can make a proton, or if you put three of them together in a different way, you can make a neutron, and protons and neutrons together make up a nucleus, and a nucleus, when it's combined with electrons, give what we call atoms, and as we know, atoms can combine together to make molecules, and molecules can combine together to make us, as well as other objects that are familiar to us. So there's this sort of Russian doll idea. Atoms are made of smaller things, electrons are fundamental, but a nucleus is made of smaller things, and to take an atom and separate it into a nucleus and electrons take a certain amount of energy. And if we wanted to take a nucleus and separate it into protons and neutrons, that takes even more energy. And if we want to take a proton and look inside it to see what it's made of, that takes even more energy. So in other words, there's an implicit energy scale here from the top down. Relatively low energy at the top, but it takes more and more and more energy to separate these various objects as we go further and further deep into this Russian doll idea. But to a physicist, low energy and high energy mean much the same as low temperature and high temperature. Temperature is just a measure of how much energy a particle has. And remember, we deduced that the universe started hot and is cooling down, which means the time arrow is actually going up from hot at the bottom to cold at the top. What that means is, in the early universe, it was simply too hot for quarks to get together to make protons, because if you try and put quarks together and make protons, there's so much energy, in other words, the temperature is so high, they will just shake themselves apart. And it'll take longer for the universe to cool even further before protons and neutrons can get together to make the nucleus of an atom. If you try and put protons and neutrons together before the universe is cold, the nucleus will just shake itself apart. And similarly, you'll have to wait even longer for the universe to cool before a nucleus and electrons can get together to form atoms. If you try before the universe is cold enough, the atom will simply shake itself apart because it'll have too much energy. So there's this implicit time going from bottom to top. The universe builds itself from the bottom upwards. So where do we start? We start at t equals 0. Remember, we do not know what happened before the first picosecond. So we cannot answer the question what happened at the instant of time t equals 0. Science cannot provide a definitive answer. There's plenty of people who have hypotheses, but the hypotheses cannot be proved, and therefore it is not a theory in the sense of the Big Bang theory. So how did the universe come into existence? Well, perhaps, who knows, maybe it was a quantum fluctuation, a fluctuation in energy where you can borrow something from nothing. I mean, it sounds really weird that you're allowed to make something out of nothing. Yes, it sounds weird, but Quantum mechanics is weird. Quantum mechanics is the theory that explains how things behave on very small scales. And as best we can tell, something is being borrowed from nothing all the time. So maybe this is what happened at t=0. Something was borrowed from nothing and the universe was created. How much can you borrow from nothing? How big can this so-called fluctuation be? Well, if you want to borrow a certain amount of energy, then the energy multiplied by the time over which you borrow the energy has an upper limit. It's a bit like borrowing from the bank. Because of interest, you can borrow a very large amount of money for a short time because the interest will be crippling, or you can borrow a very small amount of money, in which case the interest is rather smaller, and you can pay it back over a longer period of time. It's sort of the same with borrowing energy from nothing. So you can borrow a lot of energy for a short time or a small amount of energy for a long time. How much energy do you think we had to borrow in order to make a universe? Well, it's only an estimate, but we have attempted to estimate the total energy of the universe. If you add up all of the gravitational energy and all of the matter energy, the energy of matter in the universe, it looks like the answer might be 0. So if the total energy of the if the total energy in the universe is 0, then we've got as long as we like to pay back the loan. I'm sure that sounds like a cheat, but that, to be honest, a lot of quantum mechanics sounds like a cheat because we're not used to thinking about the world in terms of how things behave on the microscopic scales. But remember, this is just hypothesis. We do not know. After an unimaginably small time of that many zeros with a 1 on the end, 10 to the minus 35 seconds, the universe expands until it's about the size of a golf ball. And what do I mean by that? Well, the observable universe at the moment has a diameter of about 100 billion light years. Approximately speaking, we can see what's going on inside a sphere of diameter 100 billion light years. That's the size of the observable universe. But if the universe is expanding, then it used to be a lot smaller. And we think that everything that used to be in the observable universe that we can currently see used to be in a volume approximately the size of a golf ball. It's difficult to imagine just how you would get 1 trillion galaxies, each of which is 100 billion stars, crush that down until everything is squashed into the size of a golf ball. It's impossible to imagine, but it is believed that that's how it started. Just like a golf ball, at the time the universe was not perfectly smooth. It had dimples in it. Now a golf ball has dimples in the surface. The analogy is that the universe was not totally uniform, but had small variations of density and temperature across its volume. Eventually, when the universe expanded to a much, much, much bigger sphere, these little variations in density spread across the universe and formed the large-scale structures that we now call galaxies and clusters of galaxies. We'll see a simulation of that in a little while. Let's move forward to 1 picosecond, 1 trillionth of a second. 1 picosecond after the Big Bang, the universe has expanded to approximately the size of the solar system. Yet the solar system doesn't exist yet, but this is just to give you an idea of scale. It's gone from the size of a golf ball to the size of the solar system in a time period of 1 trillionth of a second. Yes, it is expanding much, much, much faster than the speed of light. The temperature would now fall to about 10 to the power 15 Kelvin, and the energy of each of the constituents of the universe, let's call it quarks, it's actually going to be a mixture of fundamental particles that were made from the borrowed energy. It could be quarks, it could be electrons, it could be lots of other exotic particles, but just for simplicity, let's just call it a soup of quarks. So the constituents of this quark soup are at a temperature of 10 to the 15 Kelvin. Now that of course is very hot, but we can effectively generate those sorts of temperatures by accelerating particles in the Large Hadron Collider. In other words, the energy of each of the particles at this point, 1 picosecond after the Big Bang, are equivalent to the energy of particles that we can generate here on Earth. In other words, we can test our theories. If we have an idea of what was going on at this point, we can test it by generating those energies and banging particles into each other to see what happens. That is why we say that from this point onwards, we have a reasonably good idea of how the universe evolved, because from this point onwards, the temperatures are accessible by accelerators accelerating particles to equivalent energies. If we borrow energy, we can make matter, and energy and matter are continually exchanging back and forth. I say matter, but technically it should be matter and antimatter. Every particle has its opposite. Every electron has an anti-electron. Every quark has an anti-quark. Every particle of matter has an equal and opposite particle of antimatter. Originally, they were made in equal amounts. I don't know how to express energy, so I'm just going to write energy as a big capital E rather than try and come up with a clever picture that expresses energy. So energy generates a particle and an antiparticle. It could be a quark, it could be an electron, it could be, well, it's probably not going to be a tangerine. The point is, it doesn't matter what it is. It generates some particle of matter and its opposite, antiparticle. So it doesn't matter whether it's a quark or an electron or a much more exotic particle, it generates something and the anti-something, which then annihilate with each other and generate energy. And that energy can then be used to make another particle and an antiparticle. Not the same one again, it could make a completely different particle and an antiparticle. Probably not a hot dog and an anti-hot dog, but the actual thing it generates is not important. Energy is converted into matter and antimatter. Matter and antimatter annihilate to generate energy, which then generates more matter and antimatter. Back and forth and back and forth and back and forth continuously. Via a process that we don't properly understand, somehow matter gained a very small excess. We think that they should have been made in equal quantities. Every time you generate a particle of matter, you should generate a particle of antimatter. But somehow matter gained a foothold over antimatter. And that meant that when you generate a lot of matter, you didn't generate quite the same amount of antimatter. I've shown the excess here as sort of 10% or so to allow it to be visualized. It wasn't so large. The excess wasn't 1 part in 10. The excess was more like 1 part in a billion. So matter and antimatter were made in almost equal quantities, but there was a slight excess. Which means at this particular time, after a picosecond or so, matter and antimatter annihilated to make energy, which ultimately is in the form of light, for electromagnetic radiation. Let's just call it light for short. So there's a lot of light, but notice that the last piece of matter cannot annihilate with an equivalent piece of antimatter because they're not in balance. So we're left with some matter. So at this point, and from this point onwards, the universe comprises a lot of radiation, a lot of light, and a small amount of matter. So there are a very large number of photons for every particle of matter. But the matter, remember, is everything that we can see. It's you and me and the Earth and the Sun and the Milky Way and the Andromeda Galaxy and all of the galaxies that we can see, as far as we can tell, are made of matter, not antimatter. And for every particle of matter, there's a billion photons floating around. So it's just as well there was an imbalance, otherwise we wouldn't be having this talk. Let's move forward 1 millisecond after the Big Bang. Matter and antimatter are continuing to pop into and out of existence. Protons and neutrons are made from quarks and they're continually transforming into each other. So By made from quarks, what I mean is quarks have different types, and I'm not going to explain what the different types are. I'm not going to talk about why some of them are labelled with a U and some of them are labelled with a D. I'm not going to explain why some of them appear to be coloured red, some green, some blue. All that we care about is that if we have three quarks of a particular type, then when they get put together, we call that a proton. And if we take three quarks and put them together in a slightly different way, we get a particle that we call a neutron. So a proton and a neutron are just the names we give to a bag of three quarks of this type or a bag of three quarks of that type. And quarks are continually changing backwards and forwards. Quarks and antiquarks are annihilating to make energy, which makes more quarks and antiquarks. The bottom line is protons change into neutrons and neutrons change into protons because energy and matter are continuing to exchange back and forth and back and forth. So protons and neutrons have been made, but they are continually moving backwards and forwards. Their character, their labeling, their nature, if you like, is in a state of flux. But if we move forward to about 1 second after the Big Bang, the universe has cooled to about 1 billion Kelvin. And it's now too cold for protons and neutrons to readily swap back and forth. Up till this point, there's been plenty of energy in the system, and protons can change into neutrons and neutrons can change into protons back and forth and back and forth. But now it's a bit too cold for that to happen. So what we find is that at this point, approximately 1 second after the Big Bang, because protons are a little bit lighter than neutrons, protons outnumber neutrons. So how do we know that protons are a little bit lighter than neutrons? Well, because we can measure them in the laboratory today. And a neutron now is no different fundamentally from a neutron 13.8 billion years ago. And similarly, a proton now is fundamentally no different from a proton 13.8 billion years ago. So if currently neutrons, which are represented by these blue circles, are heavier than protons, which are a little lighter than neutrons, not by much, only by 1 part in 1,000, 0.1% difference in the mass of these. But at this point, 1 second after the Big Bang, the universe has made more protons than it has neutrons. Why? Because it's easier. They are lighter. Nature always favours the lower energy, or in this case, the lower mass, because energy and mass, if you like, are sort of equivalent here. So because protons are a little bit lighter than neutrons, the universe makes more of them. And these circles on the right-hand side here represent the ratio, 3/4 of protons to 1/4 of neutrons. So in this little batch of 16, I've labelled them here with 12 red and 4 blue. So we now have a universe which is made of 3/4 protons, 1/4 neutrons. Now we move forward from 1 second to a couple of minutes or so. Neutrons are unstable and some will decay. How do we know that neutrons are unstable? Because we can watch them in the laboratory and we see that they are unstable, that they can change into protons. And we can work out that the ratio of protons after a couple of minutes or so will change from the original set I had, which was 12 lots of red and 4 lots of blue. It now changes to 14 lots of red and 2 lots of blue, because 2 of the blues will have changed into red. 2 of the neutrons will have changed or decayed into protons. The universe, after a couple of minutes or so, has now cooled to 100 million Kelvin. So it is now cold enough for nuclei to start to get together. Up to this point, protons and neutrons have been separate particles. If they wanted to get together, it was simply too hot, they would have flown apart again. But at this point, after 2 to 3 minutes, the universe is cold enough that when neutrons and protons to get together, they can stick. And one of the most stable structures that the universe wants to create is called an alpha particle, or if you wish, a nucleus of helium. It's 2 neutrons and 2 protons, as indicated down here on the right. So this structure of two protons and two neutrons is the most stable structure you can get by mixing these various particles together. So out of these 16 particles that I've shown here, 4 of them form a nucleus of helium. So they've married up, if you like, with the neutrons. But that leaves us with 12 bachelors, because there are no neutrons for them to pair up with. There's this imbalance between protons and neutrons. So at this point, we end up with 12 protons, which another way of writing proton is the nucleus of a hydrogen atom, because that's all the proton is, it's the nucleus of hydrogen. We end up with 12 nuclei of hydrogen and 1 nucleus of helium, 2 protons and 2 neutrons. And that's it. After 3 minutes, the relative abundance of hydrogen and helium is now fixed. It cannot be changed because from this point onwards, the universe is too cold. It hasn't got enough energy to change this. And the question is, well, if the Big Bang Theory is correct, then it ought to be possible to look out into the universe and see how much out there is hydrogen and how much is helium. Yes, some stars have been taking hydrogen and converting it into helium, but actually that's only a relatively small fraction of the total. If we look and estimate how much of the universe is hydrogen and how much is helium, we find that it's the ratio indicated here. If you look in terms of mass, you can see that we've got 12 units of mass of hydrogen and 4 units of mass of helium. In other words, 3/4 hydrogen, 1/4 helium. That is the mass ratio we find when we observe hydrogen and helium abundance in the universe. And that's explained by the Big Bang Theory, saying that that's what you would expect to happen after 2 to 3 minutes. That ratio will be locked in, and that's what the universe will have for the next, I don't know how many trillion years. It'll slowly change because some stars will start making more helium. But for billions of years, that ratio is effectively locked in. So that's what I mean when I say it took 3 minutes to make the universe. It took 3 minutes to make all of the hydrogen and helium, which ultimately will then power all of the stars in all of the galaxies in the observable universe. We're now going to jump forward because nothing much interesting happens for the next 1/3 of a million years. We're going to jump to 377,000 years into the future. The universe during all of that time will continue to expand and continue to cool. At this particular time period, it's been calculated that the universe will have cooled to about 3000 Kelvin. Why is that an important temperature? Because at this particular temperature, a nucleus can hang on to its electrons, and so atoms can exist for the first time. Up to this point, any nucleus, simply if you tried to get electrons to stay orbiting the nucleus, the positively charged nucleus and the negatively charged electrons buzzing around them, up to this point the universe was too hot and the atom would simply ionize and fall to pieces. But now the universe is cold enough for atoms to exist for the first time. So the universe changes from an ionized plasma with separate positive and negative charge. It's now a collection of neutrally charged atoms. And because atoms have no net charge, this is the point at which the universe becomes transparent to light. Up to this point, the universe was a plasma which stopped light moving around. Light was effectively trapped inside the plasma. But now the universe is transparent, the light is free to fly around the universe. And we can see that light today, that light that was released when the universe turned transparent. It was originally, if you think of 3000 Kelvin, of course, anything that's at 3000 Kelvin is going to be white hot and emitting a huge amount of visible light. But we don't see it as visible light, because in the time from this particular era we're talking about to the present day, the universe has expanded 1,000-fold. And so originally the wavelength of light would have been perhaps a fraction of a micron or so. Visible light has got a wavelength of about a micron, but now that light is 1,000 times longer in wavelength because the universe has expanded 1,000-fold since then. What light is 1,000 times longer in wavelength than visible light? Well, it's light with a wavelength of millimeters, not microns. It's microwaves. So the afterglow, if you like, of the Big Bang that was released when the universe turned transparent, that is the cosmic microwave background. This is an all-sky map where the sky is unwrapped into this ellipse, and the light is coming from all directions. There is a small variation. It's essentially the same intensity in all directions, but there are small variations. I've indicated here red is slightly higher intensity and blue is slightly lower intensity. It's only parts per million or tens of parts per million. So it's essentially the same temperature throughout the entire sky, but there is a small variation there. And the cosmic microwave background that we observe is not perfectly smooth, and it is those variations that are quite interesting in themselves, because those variations are essentially the dimples in the golf ball that we saw quite a few slides ago. Small variations in density and temperature in the cosmic golf ball have expanded to show us those variations in the cosmic microwave background. And that's why studying the cosmic microwave background is so important. The more precisely we can understand those hot spots and cold spots in the microwave background, that helps us understand the very early state of the universe. So let's just give you a little simulation to give you an idea of how that happens. I said earlier that those dimples in the golf ball, given time, given gravity pulling on the higher density regions, it will effectively form the galaxies that we observe. Let's just run a simple simulation. This is called the TNG project. I've given a little web address at the bottom if anybody wants to follow this up. We can imagine that we've got this simulation which is a small chunk of the universe, and there are small variations in density and temperature. You can perhaps just about see a small mottling of colour in the background. Darker colours and lighter colours represent slightly different densities and temperatures. If that's what the early universe looked like, and then we allow gravity to do its thing, what happens? Well, gravity exaggerates those density variations and starts pulling matter together. And the brighter spots here represent the densest regions of what is now forming a cosmic web, a web of filaments. And where those filaments intersect with each other at these white knots, that's where galaxies and clusters of galaxies are starting to form. So there were some regions that appear to be relatively low density and some regions which appear to be relatively high density. If you start with a small variation and let gravity do its thing over a few billion years, this is what simulations tell us the universe ought to look like. And if you remember that fly-through that I showed you very early in the talk, the universe is indeed not uniform, but we do see clusters and superclusters and lines or filaments where lots of galaxies seem to form, and we do see areas which appear to be relatively devoid of galaxy formation. If we look at what's going on around our own Milky Way, for instance, this is our immediate neighbourhood, the local group. There's the Milky Way, the Andromeda galaxy over here on the right. And we see quite a few smaller galaxies around us. If we zoom out a bit, so the local group now is just in the centre part of this particular area, we see that there are various clusters and superclusters close to us. Notice that again, this particular region, this particular volume is not uniformly spread with galaxies. There are quite definitely high densities in some region and low densities of galaxies in other. If we zoom out one more step, then we can see that we are buried right in the middle here somewhere, and you notice that there are various clusters and superclusters forming these filaments. Over on the right hand side here we see a region that appears to be populated with very few galaxies, one of these voids if you like. This is all a consequence of the dimples in the very early golf ball being manipulated by gravity such that we end up with a cosmic web of filaments and voids where galaxies and clusters of galaxies will form. What happens in the next 13.8 billion years? Well, if we say that in 3 minutes we can understand where all the hydrogen comes from, then once we've got hydrogen, we can understand, well, most other things. If we know where hydrogen comes from, we can understand galaxies and stars and planets and trees and mountains and snowflakes and rainbows and cats and okay, maybe not cats. I don't think we'll ever understand cats, but assuming we understand where the hydrogen comes from, then we can understand most other things. Yes, there are definitely some details of cosmic evolution that we have yet to work out, but you get the basic idea. If our understanding of physics is correct, we understand the hydrogen, and everything else flows from that. Let me just give you a graphical summary on a ridiculous timeline going from the very short to the very long. We said that in the very early universe we don't understand what happened at t equals 0, but after a very short length of time we think the universe might have been, the observable universe that we see today, might have been contained in a volume about the size of a golf ball, and that will have contained a quark soup. Not just quarks, it will be quarks and electrons and loads of other particles. After a second or two, those quarks will combine together. It'll be cold enough for those quarks to combine together to make protons and neutrons. A bag of 3 quarks makes a proton, a different bag of 3 quarks makes a neutron. After a minute or 2 or 3, the protons and neutrons will get together to form the nucleus of helium, and all of those protons left as bachelors will form the nuclei of hydrogen atoms. Nothing much will happen for the next third of a million years until those nuclei grab hold of electrons. By this point it's cold enough for a nucleus to hold on to the electrons and make atoms, at which point the universe becomes transparent and we see the light that's then released as the cosmic microwave background. We're not sure what happens for a little while thereafter because it takes time for stars to form after the cosmic microwave background, the background that we currently see as the cosmic microwave background. Once that light was released, it could have taken hundreds of millions of years for the first stars to form, but we don't know exactly what happened in those so-called dark ages. That's one of the jobs of the James Webb Space Telescope, is to look back in time to that first fraction of a billion years to work out what happened after the point at which the light was released and how those first stars and first galaxies were actually created. We know what they look like now. We've got an idea of what they looked like in the past by looking back in time, and galactic evolution is something that, of course, is something that we are still studying. We've got a good idea how it happens. We don't necessarily know how it started. But I don't want to give the impression that we understand everything. We've got a lot of the pieces of the jigsaw in place, but there are still a few pieces missing. There are some fundamental questions still to be answered. Why did matter win over antimatter? In other words, we thought that they were in symmetry. Something caused an asymmetry such that matter won over antimatter. Only one part in a billion, but a very important part because that's us. And I was talking about everything that we see in the observable universe, all of the galaxies, all of the stars, all of the planets, all of the dust, all of the gas. But that's, of course, not all of the universe. What about this strange dark matter that we think exists, that causes galaxies to rotate at the speeds we wouldn't expect by just looking at the amount of visible matter in the galaxy itself? And what is dark energy? The universe is expanding, but it appears to be accelerating its expansion, despite the fact that gravity is trying to put the brakes on. So we don't know what this is. We've given it a name, but we don't understand what dark energy actually is. So the talk was called The Beginning of Everything, but I've been very careful to try and talk about everything that we see in the observable universe. But everything we see in the observable universe only accounts for 4% of what we think is out there. The other 96% is still a bit of a mystery. But, as they say, that's another story. Thank you for listening.